Okay, hello everyone. Let's start today's discussion. I hope you all started a great day. Today, we are gonna try to finish the discussion about the root locus and how we can use root locus to basically estimate the time response. Uh, Before I start the discussion about the time response using the root locus, I want to mention some very quick points about how would be the effect of the poles or zeros when you have a system and you kind of like adding those poles and zeros, like extra poles and zeros in your system, and how they would affect the root locus graph that you have. Now, this is an approximation, okay? The exact effect of adding any type of poles and zeros into your system would need to run the analysis that we talked about, okay, in the previous discussion and find out what is the exact trajectory of the poles when the K is changed, okay? Now, let's say we have a second order system, and here we have two poles S1 and S2, or like P1 and P2. This is our initial second order system. Now, based on the discussion that so far we had, we know if this is the open loop poles, that means the trajectory of the case in the root locus, the trajectory of the poles based on the change in the case in root locus would include some real axis values, and then since we are short with zeros, then we are going to have some imaginary, because somewhere we are going to leave the real axis. Okay, now we know how to draw the root locus. When you have such a system, we know that this section of the real axis is going to include the poles, the trajectory, and we know that we are going to start from the poles and end up to the zeros. We don't have any zeros here, so the original root locus would end up in the zeros in infinity. Now, if you run the analysis over the when the trajectory would leave the real axis, that breakaway point, okay, I'm just going to do the estimation so you can calculate that. And the asymptote lines, okay, you can find out that first of all, we have two extra pole compared to zero, a number of zeros, okay? That means our theta of the asymptote lines is going to be plus and minus 90. You can imagine that, and you can use the formula to calculate that. So we know that somewhere here, we are going to leave the real axis, and the trajectory would end up going to the infinity with a perpendicular kind of like angle of the asymptote line. Are we good? Now, let's say I am going to add another pole here. Now, what's going to happen to my trajectory? Okay, first of all, because I have three poles, now we are going to have another section in the real axis that would include the trajectory. So that goes without saying. So you know how to define that. We are going to end up with an extra real axis trajectory. But that's not just it. Because we have now three poles, the theta of the asymptote line now is changing. Before it was pi over 2 or minus pi over 2, now it's over 3. Very good. So it is gonna, we are gonna end up, first of all, the intersection of the asymptote lines, okay, in the real axis would change, because that was the summation of the zeros minus the summation of the poles over the difference between the number of the poles and zeros. So we know if we add another number here, that means that point that we call it delta A, okay, would change. And the pole is here, so it would kind of like move away, move closer, move away from the zero and closer to the higher order pole. Is that clear? So the delta I, the new delta I, is going to end up somewhere further from the zero. Very good. And we already mentioned that the theta of those asymptotes now is divided by 3. And now that we have 3 poles, more than the zeros, we have 3 line, okay? And we already seen the examples. The new asymptote lines are going to be plus minus 60 and 1/8. Do you remember that? We already saw such an example before. So now look at this. If this is the asymptote line, now the trajectory of the poles when they leave the real axis would change to new values. Right? So what happened? I added a pole, and that pole basically pushed away the trajectory from itself. So adding a pole would push the trajectory away. Very good. Now, what would happen if instead of that pole, I add a 0 here? So I don't have this pole. This is the new case. I don't have this pole. I would have a 0 here. Now what would happen? I still have the same sections in the real axis. Sorry, this is end up in the 0. But without even talking about the asymptote lines or the whole situation that we calculated to approximate the exact value of the exact trajectory of the root locus, you can imagine that since we should end up in zeros, then these poles, one of them, okay, should go toward the zeros. There is no trajectory in this part of real axis. That means now when these poles, one of these poles leaves the real axis, it should end up somewhere so it could go to the zero. We have a symmetry. That means the other pole should have the same trajectory, but now there is no zero to go, so it goes again to the infinity. Now what happened? I added a 0, and the 0 attracted the trajectory toward itself. Does that make sense? So when you add a pole, it would basically push away the trajectory. And if you add a 0, it would attract the trajectory towards itself. Make sense? Now, if the value of the pole or zeros get higher and higher, meaning it is far from the 0, an imaginary line, okay, you can imagine that it would, like if we have a pole here, okay, now the asymptote line would move away further, okay, is that clear? And that means the scale of pushing the trajectory, okay, would decrease. So as far as these poles and zeros are, they would affect less on the original trajectory. So now, right now, if I have a pole far from here, it would push the trajectory, but the push would be much low. Same goes for the zero. If the zero are far from the original pole, the attraction would be weak. Now, how you can describe that based on what we learned before when we talked about the time response, we said each of these poles in a real axis would add up to a, when it's in the negative half cycle, would add another decay or decreasing exponential to our time response. Remember that? Because it's going to be e to the power of minus that pole time t. Are we good with that statement? Do you remember what we talked about in time response? So if we have here P1, P3 here, that means it would add another term e to the power of minus P3 times t to our time response. So that means if we are far from zero, this P is large, so the decaying term would have a faster trajectory toward the final value, a steady state value. That means it would go away very fast. So that's why, as large as when you move away from zero, the effect of the pole would decrease because it's go away very fast. Very good. So that's kind of like the point that first, before I move on to next discussion, I wanted to like let you know it help you when you wanted to like just approximate what's going to happen. Okay, it would help you a lot to see, okay, if I have a system which I don't like it, okay, if I add a zero or pole, so what would I end up? Is it better situation for me or worse situation for me? Make sense? Now, let's move on to the next discussion. Now, because we had a problem, I had a problem actually with my laptop in a previous discussion, and it didn't record the session. In this discussion, when I solve an example, I'm gonna do all the stuff that we did next in the previous session. So it's kind of like a reminder, and then you have a video record to review that. I hopefully this time my laptop would work properly. Now, what we are going to discuss today is how we can design the transient response for our system. We already talked about that we are going to have in the previous session. We said if we want to have a specific decay coefficients and a specific psi, okay, we can find the poles in our trajectory that would satisfy the goal we have for the decay. Okay. Now, we wanted to like kind of like go through the design and find out how we can actually reach that design again with an example. And beside that, how we can approximate and make our life easier, okay, when we have a high order system, like for example, a third order system. Because we already know how to deal with a second order system, and it was easy. We know, okay, the second order is at two zeros, minus cosine omega n plus minus omega n times square root of 1 minus cosine square. Remember that? So we know how to deal with that. It's easy. But if we have a third order system, now dealing with the time response would be a little bit more tricky. On second order, we know, okay, we are going to have underdamped, overdamped, critically damped, or pure oscillation based on the value of the psi and omega n. Okay, but for third order, how we can easily estimate that is hard. Now, let's do an example and see how it could help us. Now, we have a feedback system with a forward pass transfer function of k times s plus 1.5, and the denominator is s plus 1, and s plus 10. Very good. And this is the feedback, a unity feedback loop, actually. So, by g of s, the open loop transfer function or forward pass transfer function is this. So this is my g of s. The overall transfer function of the system, which is the first thing that you have to do, is going to be that g. Okay, the h is 1, that's why I'm saying g. That g over 1 plus g. Okay, the h is 1. Okay, so don't get confused that I didn't mention the h. Here is a unity, so h is 1. Now, if you run the analysis and do the derivation, you are going to see that your overall transfer function is going to be k times s plus that 1 minus half over s squared plus 11 s cubed plus 11s squared plus 10 plus k s plus 1.5 times k. So this is going to be my closed loop transfer function. Okay, now let's do some Lucas kind of like analysis. For the Lucas, we said we are going to use the open loop zeros and poles. So I am going to try to draw my transfer function. This is 1, 2, 3, 1, 2, 3, 4, 5. Let's go further. -1, -2, -3, 4, 5, 6, 7, 8, 9, 10, 11. I have a pole at 10, so I'm going to move away off until -10. This is -11. Now, I have one pole at 0. I have another pole at -1 and another pole at -10, and I have a 0 at 1.5. So my 0 is going to be here. Are we good? Now, first thing that we always did was to find out what sections of the real axis would include the trajectories, right? So we know this part is a part of our trajectory. This one is. This not. There is no trajectory here, and we have a trajectory here. Are we good so far? And the poles are moving, the trajectory move away from the poles and get into the zeros. That was the base of our root locus. Now, what would be the trajectory when they reach each other? So there is an intersection of the poles, so they have to leave the real axis somewhere. Right? Now, how we can do that? How we could find out the values for those breakaway and break-in points? We said we are going to have the condition that would satisfy the break-in and breakaway was the S's that would satisfy the differential of the K over the differential of the S equal to 0. Very good. Now, I'm not going to do the mathematical derivation. You know how to find the function K based on S. It is here. You can easily find that. Okay. Now, for my system, K of S is going to be S times S plus 1 times S plus 10 over S plus 1.5. It's very easy, actually. You can see that here. Right? Now, because eventually it's going to be equal to 1, okay? That 1 plus GH equal to 0. So GH is going to be equal to 1. H is 1. So G is going to be equal to 1. So minus 1, yes. So that then we are going to end up with the function of the K versus the S. You good? Now, you can also use the absolute value of the pulse. So the absolute value of KGH should be 1, right? Again, you can use that in order to find what's going to happen. For all the S's that you put here, K times G of that S should be 1. So K is going to be 1 over GH for those S's. So if I solve that, the case, the S's that will satisfy this condition, okay, is going to be S1. I'm going to have 3 S's are going to be minus 0.62 to minus 2.76 and minus 4.36. Okay, so I am going to have a breakaway or breaking point at minus 0.62, another one at 2.76. Are we good? And another one at 4.36. So this is 2, 3, 4.36. Are we good so far? Now, we know when the poles leave the real axis, they have to end up in 0. What that means? That means this pole that we have here, like for example, pole 1 would leave the real axis, but it has to end up to a 0. So it should go to this part, so it could end up to the 0. Very good. We have a symmetry, so the other pole should have the same trajectory to the same point, but it goes the other way. Now we have 2 poles again that intersect, and the breakaway point is this point that we calculate. So they are going to end up leaving the real axis at that point. Are we good? Now, I am going to erase this. Are you okay?
Clear. You derived KS because of like
KGH is going to be 1. So K for these S's should end up at.
didn't have to differentiate like a the past.
Yes, we have to. This is the difference. This is the formula that come from here. Okay. Now, if I differentiate, let me do this. If I take a differential from this and make it equal to 0, I would find these roots
Okay.
for that condition. Is that clear now? Any other question? No? Okay, I'm gonna erase this because I need the place for trajectories of fluids. Now, how they would behave, they are going to leave the real axis and end up to infinity. But where? And how they would move to infinity? We need the asymptote lines, right? Now, for asymptote lines, we know to do that. We know that we could find the delta A. Now, here we have three poles and 1 0, so we are short for 2. That means we are going to have 2 lines, right? So the delta, the place that those lines would intercept with the real axis, the formula for that was the, let's see if I wrote that down so I won't make a mistake. The summation of the poles minus summation of the zeros divided by the number of the poles minus number of the zeros, or vice versa. This is an absolute number. It doesn't need to be negative. Okay. Now, in our case, this is 2. Okay. The summation of the poles are 0, minus 1, and minus 10, which is minus 11. The 0, we only have 1, and it's over 1 over half, minus 1 over minus 1.5. So it's going to be minus 1.5, so plus 1.5 over 2. So this one, the delta, if you calculate that, which is easy, will be minus 4.75. Yeah. That means this one was minus 4. This one was minus 4.36. So this one is going to be somewhere here. Right? So this is going to be the delta F. So the lines would leave here, intercept with the real axis here. Now, what are the thetas of those lines? Is you can calculate that using that formula, which says the theta of the asymptote are 2d plus 1 times pi over the difference of the numbers, which is 2. And we would change the d from 0 to the 0 and plus minus 1 and plus minus 2 based on whatever we need, the number of the theta that we need, and we can find. But since this is 2, you can imagine that we are going to have a plus minus 9. Very good. So we are going to end up with 2 perpendicular asymptote line, meaning the trajectory would end up these lines. Very good. So now we have our fluids, and I'm going to eliminate these lines because I don't want to create confusion. Any questions so far? Are we good? Now, I have my fluids. What I need is to design that for a specific condition. Now, before we only talked about, what's happened here. We only talked about when we directly have the psi and how we can find the psi. Now, this time, I want to say, okay, I want the overshoot of my response to be like a certain value is a percentage. So I am going to design the system based on the target value for overshoot of, what is the value of the overshoot? 1.52%. Okay. Now, you can go over the derivation for the second order differential equation Okay, and find out if we have a certain overshoot. That means your psi could be calculated by the overshoot, and the formula for calculating the psi based on the overshoot is a little bit tricky, but you need to kind of like go over the derivation to find out this function. Is the ln of overshoot over 100 divided by pi squared plus the ln of overshoot over 100 squared. So by this formula, you can find the psi from the overshoot. And if you put the numbers in, you will find out that my psi for this targeted overshoot is going to be 0.799, which I can approximate as 0.8. Now, we said we can show the psi using a line in our root locus, right? For psi equal to 0.8, how we would find the theta of that line? It was the cosine inverse of that psi. Remember that? So if we use that value, that means the theta of our psi line should be, if you do the cosine inverse, should be 36 point, what is it? 88 degree. Are you good? Cosine of the theta was psi. I hope you remember that function and why we restarted that function. This is the psi line, for example. And let's say this is the theta. The trajectory on the real axis is the cosine of that line. So cosine of that theta is going to be the psi. Is that clear? So the reverse of that is going to be the psi is going to be cosine inverse of that psi is going to be the theta. Very good. So right now, I know if I want to have such an overshoot, I need to have a line with a theta of 36.88 degree, and this is going to be the line of my psi equal to 0.8. And we know that the poles that would satisfy our goal was the point that would intercept the point of the interception of the root locus and that line. We have 3 points. One here, another one here, and another one here. Which we could calculate that by creating the by driving the mathematical formulation of that line and the a function of the psi, function of the system that we have, the transfer function. We can find the intersection. Now, at the beginning of the discussion, we said that yes, we have a third order system, but since we don't like put ourselves in trouble and we are already comfortable with second order system, how we can estimate the time or the transient response of this system for such a overshoot that we kind of like or desire. using a second order system. Okay, now how we can do that? Now, if we consider a second order system instead of the third order system, okay, we already know that the poles or zeros of that second order system are going to be minus psi omega n plus minus, and we have an overshoot. That means we are under that because we have oscillation. J omega n over 1 minus psi squared. This is what we already know. Now, based on our goal, which was overshoot equal to 1.52%, we find out that our psi should be 1.8. So we know the psi here. But we don't know omega n of the second order system that will satisfy this condition. How we can find it? Anyone have any kind of like idea? We want these two to be our poles. We know the psi. We want to find omega n. What condition that we could use in our system to find omega n and find out what's going to happen in our second order system? What was the condition? These are going to be the poles of our system, our second order system. What was the condition for the poles? Any point in our locus would be a point if there were two conditions. What was those? Yeah, go on.
Like a multiple window.
The theta of those zeros and poles, okay, should be the summation, like the zeros minus the poles, should be end up an odd number of 180. That was one of the conditions for the SS to be a pole. Now, we want to have a second order system, but we didn't lose our zeros. Having a second order instead of third order, that means just the denominator. We only approximate the denominator from third to second order. Good. So we have 1 0 at minus 1.5. What would be the theta of that 0? The 0 is minus 1.5, meaning it is plus minus J0. What is the theta of that? Tangent of the imaginary part over real part, okay? The tangent inverse is going to be the theta. Imaginary part is 0. Tangent inverse of 0 is 0. So the theta of this 0, so this one is going to be minus, this z is going to be minus 1.5 with 0 degree. Very good. Now these two s's, they have imaginary part, but we already know how the theta works. Correct? So if we want to satisfy the condition for the poles, that means the angle of the 0, which is 0, minus the angle of S1 plus angle of S2 should be equal to the odd number of 180, let's say 180 itself. These two are a function of omega n. So by solving this equation, we can find the values of omega n that will satisfy this condition. It's a little bit of a hard kind of like mathematical derivation because we have a tangent here. Okay, but it's not impossible. So if you run this analysis, you are gonna see that omega n is gonna be 1.1 radian per second for these two poles. So our psi we already know is 0.8, and based on the poles angular condition, we can find the omega n for that second order system. Are we good? Now we have our S's. So based on these values, our S1 and S2 are going to be minus 8 times that omega n, which is minus 0.87 plus minus j 0.65. Very good. We find omega n. We know the poles are here. We know the psi, so it's just a that's the multiplication. We find the actual value of S's. Is that good? No. We also know, so you see, this is going to be somewhere here. Let me actually show that in the graph, in this root locus. Minus 0.87 is here. Okay. And 0.65, this point was 0.62, this interception. So 0.65 is going to be here. My drawing is off, but you can find that these two S's actually are this interception and the conjugate of that interception.
So how did you derive omega n?
This is a condition that says if it's met, these two S's are going to be poles. Okay. Now, the theta of those S's, the theta of these S's, the theta of S1, for example, is going to be the tangent inverse of my omega n 1 minus psi square over psi square omega n. Are we good? Now, the next one, this is minus. The next one, the S2 is just, this one is also minus. This is plus minus, right? So you have two tangents. Okay, and you can find the values based on the function that you have. Does that make sense?
I'm not clear on how you got one.
This is a function of omega n. A tangent inverse function of omega n. Same as this one. So you have a function of omega n equal to 180. Now, for these S's that I find, if you look at the root locus of our original system, you would see that it's actually one of the interceptions. So what that means? That means that second order is within our trajectory. So we actually can use that to estimate our third order system and find out how it would satisfy the condition. So instead of solving that third order for that condition, we replaced it by an unknown second order system, or estimated by that unknown second order system, and find out that the condition or the values of the poles that would make that second order meet our targeted values, okay, are a certain poles. And if you look at the third order Lucas, those are actually one of the interception of the Kasai we need and the third order trajectory. Are we good? Is that clear? We had a third order system and we wanted to meet a certain Kasai. We know to meet that, our poles should be one of these interceptions. Are we good so far? Now, how to find those? Instead of solving the third order system to find those interceptions, okay, we can imagine or take advantage of an unknown second order system that also would satisfy the same condition. Okay, now that unknown system, if it wanted to satisfy this condition, should have a certain psi and a certain omega n. Based on the condition itself, we know what is the psi is. So if we find the omega n of that unknown second order system, then we would end up with a specific known second order that satisfy our targeted condition. Are we good? And we know that if the zeros of that second order, which are the poles of our system, are going to be actually a pole, they should satisfy the angular condition of the poles in root Lucas. So the theta of the zeros minus theta of the poles should be equal to odd number of 1/8, odd coefficients of 1/8. We solve that to find the omega. We solve that condition to find the omega. Now we knew the psi. Now we find the omega, and so we have a specific known second order that satisfy our targeted equation or targeted condition. That known second order would have two poles. Now that we have a psi and omega n, we can find those two poles. But funny enough, if you actually find those two poles, you would see that the poles are actually one of the interceptions. That means that second order system is actually the one that we use for estimation, is actually could closely represent this third order system when we want to meet that condition. So instead of analyzing the third order, now we have an easier second order system to analyze. Is that clear? Are we good now? Any question? No? Now, let me use another approach. Right now, we consider a second unknown second order system and find out what's going to happen in our second order system. But so far, we know we have 3 interceptions. So that means we have 3 conditions for K in our third order system that would meet our targeted value for origin. Now, we find the one by estimating it with that unknown second order, but who says that this one, this condition, is the best condition between the 3? Is that clear what I'm saying? So yes, we find that, and okay, that would be enough for us to, like, you know, deal with the system and find the one that we need, the system that we need. But who says this is the best option? Now, let's try another approach. Before we talk about the using that second order, we said, okay, we have an interception and we can actually find, mathematically derive the whole situation and find the values of those interceptions. Very good. Now, if you actually find the values, you are going to see that this one, we are not using the second order. We're just directly finding these interceptions. This value, this point here, is going to be minus 0.87 plus minus j 0.66 or 65 something. This one is going to be minus 1.90 plus minus j 0.9. And this one is going to be minus 4.6 plus minus j 3.45. For each of those situations, remember, I wanted to make it specifically clear. This pole here is a specific case of our transfer function, okay, for a specific k. So for example, is k equal to a, the system would change in a way that the pole becomes, like for example, minus 0.87 plus minus that j. If the k is equal to another value, okay, which is gonna be a bigger value because the trajectory is moving, we are gonna end up in this point. And for another value of the k, we would end up in this one. So each situation is different system. It is different transfer function for different value of the k. Are we good? Now, do you remember that? Let me be perfectly clear. I don't want to have any confusion. That was our closed loop transfer function. Now, the poles are minus 4.6 plus minus j 3.45. If the poles of this function is going to be those two, okay, two of the poles would be those two, we can find for what value it would meet the poles at that point. Is that clear what we're talking about? You remember that k is 1 over gh on a specific pole. So if we have a pole, for example, minus 4 j 3.45, okay, that means if we put that number in our transfer function instead of the SS, okay, we can find the value of the denominator, which is the GH, okay, sorry, 1 plus KGH. Very good. And based on that, we can find the value of the K, because KGH on those poles should be equal to 1. So 1 over GH on those poles would give us a K. Very good. Now, if we run that, we would find out that for K equal to 7.0 36, we would end up to these points. This is plus minus j. This is 1 point. They have conjugate, okay, value because we have symmetric kind of like situation. Okay, so don't get confused because just I put two numbers for 1 point. Okay, I mean point and its conjugate. Now for k equal to this value, we are going to end up in our trajectory at this pole. For this pole, k should be 12.79. And for this one, k should be 39.64. Now, so now we know we have three choice to specifically design our third order system, the feedback that we have, in order to meet our condition. Is that clear? Now, which one is the best one? Which one is going to be the best one? Considering we don't want to analyze the system as a third order, we want it to have an easier life, and we want it to be able to represent that with a second order system. So we want to find the best option because all three would satisfy our condition. We already know that. What is the best option that gives us the ability to have an easier life? So for further analysis, we could replace the whole system with a second order and run the second order analysis. If we have, let's see, which one is the better estimation, which one has a better estimation of second order. For each of those cases, E2 and 1. For case 1, we are going to have, if we have a second order system, okay, the poles of the second order system are going to be minus 0.8 plus minus 0.66. Are we good? That was the second order equivalent for these 2 points. Now, if that's the second order system for the k equal to 7.36, what would be the third pole value, okay, that would affect that second order system? Let me restate that. We have a second order system with these poles. At the beginning of this discussion, we said if we add a pole, it would change the trajectory and the behavior of our system. Now, let's say we have a second order, and now we add this pole, okay, and we wanted to see how it would affect our system. The best option is that pole would have minimum effect. So the second order is the best, is the very good estimation of the third order when we have the third pole. Is that clear? What I said. So we want the third pole to have minimum effect on our estimated second order. That way, the second order is very close to the third order, and we can use it for further analysis. Now, for the case 1, k is 7.36. If k is 7.36, what is going to be our third pole? Because the third pole is also moving, right? Here is k is 0. If k is that, k1, what would be the value of the third pole? We can easily find that. We put the k here, We find the values of the zeros, and we already know 2 zeros, so we can simplify this one, because there is going to be a second order term with those zeros. Okay, so you can basically factorize that second order system, and you end up with one simple first order term, extra first order term. Makes sense? It's easy to find that. For case one, the third pole is going to be, if you calculate that, is going to be minus 9.25. And it is in the real axis, we know that. For that case, okay? Very good. For the case two, when the K is 12.79, again, we can find the third pole, and the pole, if you find it, the pole would be minus 8.61. Very good. Case three, the third pole is going to be minus 1.8. Now, we said further away from the zero line would have less effect. So these two would have less effect on the second order system when we still have the zeros. We didn't affect the zero. Our transfer function still have a zero. Are we good? So if we choose these two cases, we are going to end up with a good approximation second order system that also has minus 1.5 zero. Is that good? Is that clear? Now, between the two, which one is the better? The first one. But we still end up with a second order system with a zero. That zero also affect our time response. You know that. Are we good?
Each of those cases correspond to the K1, K2, and K3 that we calculated.
Yes, this is basically, see, this is our first second order estimation, second order estimation, and third order second order estimation. Now, if the poles of second order are this one, it would only happen when K is 39.64. Okay, so if the K is that, we can calculate the third one from transfer function. So now for the case three, we have three pole minus 4.6 plus minus J 3.45, and another pole at minus 1.8. Third pole for our case three. Same goes for the case one and case two. Are we good? Did I answer the question?
Yeah,
Is that clear, or do you still have?
maybe I just need to actively get a better.
Yeah, you can replace the K. For example, for case one is 7.36. Okay, so this one is become 13.36s plus 1.5 times that is going to be somewhere like 10. Okay,
Yeah,
is that clear? So now you have a third order equation, and you know two of the poles are those two. Okay, so if the two of the poles are those two, you can basically simplify this. There is going to be some S plus P3 times the second order system that the poles are that. And you know how to find that. It's going to be, this one is going to be 3 if you put, this is the second order, okay? So this is a second order system, okay? And you can find the values. If the zeros are that, you can find the actual function. Okay, and you don't need to actually consider that because you already know the zeros, so you only need to find this P3.
Okay.
Now, we said these two are good cases if we don't have problem that having a zero. Are we good? Now, in the third case, the pole, the third pole will be 0.1.8, which is here. Very close to that zero. Very good. Now, if we have a transfer function, an unknown transfer, let's say h of s, we have a zero, s plus a, and we have a pole here, like several pole, s plus b, s plus c, okay? And we have an s plus a hat. When the a hat is very close to the a, or let's say it's epsilon, I don't want to say zero, it's very small number. How we can simplify this h of s? If we have such a condition, we have a zero at a and a z and a pole at a hat, and we know these two are very close to each other. What we can do? With an approximation, because eventually we are approximating, okay? We want to like approximate the third order with the second. If these two are close to each other, we can, by a certain approximation, we can let them cancel each other out. Are we good? Is that clear? What that means? That means if you have a zero and pole in close to each other, very close to each other, basically they will cancel each other out. You can approximate that these two cancel each other out. Are we good? Now, if in this case we have a pole at minus 1.82, what would happen to our transfer function? We would end up with a second order system because here is our transfer function. This third one would cancel out the zero, okay? And we would end up with a k over that second order system. Is that clear? So what happened? In this case, we ended up in a second order system without any zeros. So pure second order. Now, which one is better option if you want to approximate the system with the second order? Without a zero, because now the zero would not affect the response. When you had a zero, the zero would affect. Now, case one was relatively good because the third pole would die really fast compared to the other one, right? So it would not dominate the system. But if we choose that, we also have a zero that would affect the system. So we don't have a pure second order system. We have a second order system with a zero. The next best choice was the P2, the case two. Still not dominating, is not as good as the first one. It's still not dominating. So we would have a second order system, but we have a zero also. But at the third one, P3 is within the range of domination. But the good thing that we have a 0 very close to it. So those two cancel each other out. So this is not actually affecting our system. So these pole 3 and 0 would cancel each other out. Now we have an exact, not exact, is a very good approximation of a second order system for our third order system. Is that clear what happened? Any question about that? Again, for the case 1 and case 2, we find the third pole. They are not dominating pole because they are far away from the rest of the poles. Are we good so far? But the pole does not affect much in our dynamic, so we can ignore that. But we also have a 0 that we cannot ignore that. So we have 2 poles and a 0. Same goes for the case 2. It's not as good as case 1, okay? But still, it would not dominate much. So we would end up with the 2 poles and 1 0. For case 3, the pole is within the range of domination because it's very close to the rest of the system poles. Okay, but it is so close to our 0 that we can basically see that we can say that this third pole and that 0 that we have, they cancel each other. So if they cancel each other, that means we don't actually have these two. We only have these two conjugate poles, which is a pure second order. So if you look at this, case 3 is going to give us the best option, okay, of a second order system that would approximately follows the same dynamic of our original third order. So if we analyze this case 3, the second order system with these poles, okay, we are good, and we basically analyzed the original third order system with a certain limited error. Is that clear? So that's how we can approximate a high order system with a lower order, kind of like a transfer function or system, which is easier to analyze when you want to like run the whole like a stability analysis, transient response, steady state, all those things. Any questions? No? Now, I want to add a very quick concept, and then we are finishing with the root loops. So far, all the system that we saw was for the case of negative feedback. Now, I want to ask you what would happen. What would happen if I have a positive feedback? So I have my g of s, kg of s actually, my h of s here, and this is a positive feedback. Now, what would be my transfer function? We already know for positive feedback, it became k g of s over what? What is the denominator? 1 minus kgh. Very good. Now, do you remember the discussions that we had for the condition of the poles? For the feedback loop, KGH would become 1 instead of minus 1. Right? What is the theta of 1? One is here. For example, I forget about the unit. Let's say it's 1. What is the theta of that vector? What is the theta of this vector? This is your real imaginary axis. This is 1. This is the vector. What is this theta? Theta between the vector and the real axis.
0.
It's 0. What else it can be?
What else?
What else value you can have?
360.
360. 720. So it's gonna be the theta of our pole, or of that satisfy the pole condition. Now instead of odd number of 180 is any multiplication at the even multiplication. So now the theta of KGH is gonna be 2D times 360. Or D times 360, it doesn't matter, because it's gonna be 0, 1, 2. Very good. What about the value? What about the amplitude of KGH? For the poles. The poles satisfy this function. KGH is equal to 1. What is the amplitude of KGH for the poles? What is the amplitude of the right-hand side equal to? So sorry, the amplitude of the left-hand side is equal to? This is an equation. This is equal. We want to see what is the amplitude of the left-hand side. Based on this equation, what would be the value of the amplitude of KGH? Look at this formula. What is the value of the amplitude of KGH? Have equation. Left-hand side, right-hand side. The amplitude of left-hand side, if it's equal, the amplitude of this is the vector, right? This one is a vector. With m theta. This one is also a vector that says 1 with a theta of d times 360 that we find, right? 0, 360, whatever. What is m equal to? These two vectors are equal to each other. What is the relation of the amplitude with each other? If the two vectors are equal to each other. The same. So the amplitude should be 1. So it doesn't change. It's the same as before. Correct? But the theta changed. If the theta changed, do you remember when we talked about finding the portions of the real axis for the root Lucas? The reason that we said the sections of the root Lucas in a feedback loop would be included in trajectory when you have an odd number of poles or zeros at the right was because of that 2d plus 1 times 80, right? Now we have a different value. With the same concept, if you have a positive feedback, the real part section that would be included in the trajectory of the positive feedback, okay, would be the one that has even number of the poles and zeros at the right. Because now it should equal to 0, 360, you know? So any poles here would have a 0. Any poles here would have 180. Any poles here would have, again, 360. So it's reverse, kind of like behavior compared to the negative feedback. The symmetry is still the same. Okay. The asymptote line are still the same. The theta of the asymptote line now satisfy different condition. Before we have odd multiple of 180, now we have multiple of 360. So when you wanted to like calculate the theta A for the asymptote lines, now you have 2d pi over the denominator instead of 2d plus 1 times 180. Are we good? So when you change from the negative half side, negative feedback to the positive feedback, the condition of the theta would change. So anything that you had before that you use the theta to find it or define it, now it changed. Amplitude doesn't change. Are we good? Any question? So by that, now we finish everything about Lucas, and basically we can move toward the next discussion.